Hello and welcome back to another LeetCode recording. This time we're dealing with LeetCode 33, search and rotated sorted array. This is a classic problem. Everybody who's preparing for interviews needs to know this and practice this one, I believe. And it's a medium problem. So let's just get into the interview practice with this. So first thing we want to do is check out the problem description to understand what we're being asked. And yeah, let's do that. So there's an integer array nums sorted in ascending order with distinct values. Very nice. Prior to being passed to your function, nums is possibly left rotated at an unknown index k, but at least by one position, and it's also guaranteed that it's not rotated by the number of elements in the array. So we actually have a shifted array always. Okay, such that the resulting array has the form, and this is the form. So the value at nums k is now at position 0, and that's why it's basically left shifted, right? We moved all the elements k steps to the left. So nums at 0, and then we have to go all the way to nums k minus 1. And so this is now the minimum element in the array. It's at what position? At position k, yeah, I think. For example, 1, 2, 3, 4, 5, 6, 7 might be left rotated by 3, meaning that so 4, 5, and 6 and 7 are at the beginning, and then we have the remainder of the last 3 elements. So the minimum is actually not at position k, it's at position length minus k. That's why that is. Given the array nums after the possible rotation and the integer target, return the index of target if it is in nums, or -1 if it's not in nums. You must write an algorithm with all of log and runtime complexity. Well, we're never given this in an interview. It's but this gives us a hint that this is probably the optimal solution that we need to implement. And that probably, I mean, if the array is sorted, finding a value in it, you can do that with binary search, right? In log n time. But if it's a rotated array, we have to come up with some smarts on how to still be able to use binary search on this. And this is the core of this problem. So yeah, well, the naive implementation would be O of n time, right? And O of 1 space. And just for the sake of completeness, I'm just going to write this down. And O of 1 space. And that would simply be, well, we just iterate over all of the elements in the array. For idx value in enumerate nums. If value equals target, return the index. Otherwise, we should return -1. Yeah, return -1. So let's just test this. Right, so that works. And if we submit this, yeah, it's accepted. So that works. Okay, so this is the brute force, quick and dirty approach. Now we want to go down to O of log n time. O of log n time. And if we use log n time, we're not going to use O of n space, because space can never be larger than time. It's impossible. So what we have is we probably have still constant space. I don't see us having to increase that. But the challenge is now really finding where the minimum is. If we know where the minimum is, we can just use binary search. So I have to think a little bit of how we could find the minimum. But what we can already implement is basically the binary search. And then all we need is just the index of the minimum element to know between which values to do the binary search. So we can actually have a 2-part implementation, right? Where we do, well, we could do find target, right? In a rotated array, and we just pass in our array, and we pass in the index of the minimum element, right? So yeah, we could call this offset, right? And then we just perform a regular binary search. So we have what we have with the length. Well, yeah, so we start with left and right. That is equal to, well, the left is the offset. Well, actually, to be completely honest, we don't have to care that much about it, but we just need to incorporate the offset in our calculation. So we'll still do this. So we just have a regular implementation of a binary search. Length of nums -1. And while left is smaller or equal than the right value. And then we compute the mid value, left plus right. By the way, you should be able to do this in your sleep, how to do the binary search, right? If nums at, well, the mid value equals target, we're going to return the mid value. Let me think. But now, since we have an offset, we need to incorporate that somehow. Yes, we can manage the range with left and right and those values, but we need to translate that to the actual offset in the array, right? So we say idx equals, and now comes the magic, offset plus mid, and then we do that modulo length of nums. So this computes the actual position of the mid element in our k rotated array, right? Well, with our offset. And then we just have to check values using that idx. So if that is our index, we have to return that index. And then if nums at idx is smaller than target, we do that. And otherwise, we know that nums at idx is larger than target. So if it's smaller, what do we do? Well, we set left equals mid plus 1. Otherwise, we do right equals mid -1. So we cut the range in half. So that guarantees us the log n time. And this trick with the index allows us to access the right element. So, okay. And otherwise, we return -1 if we don't find it. Cool. So, yes. So we can just, I guess, return, find target, nums, but we have to compute our offset. And for that, we need another function. And let's call this find min index or find offset, whichever you prefer. And we pass in the array nums. And well, we have to do a bunch of magic here. But we can then pass that to our basically to our function. So this would be the offset. And you can write that however you like, or however you prefer. Cool. So now we need to find the minimum element. And how can we do that? Well, we will use a strategy that is similar to binary search, or kind of follows the same idea, right? We will have a left and a right pointer, and they actually point to the left and right side of our nums array. -1. And well, while left smaller or equal to right, we're going to do something. So we're going to compute our mid value again, left plus right, and integer division as always, right? So now what do we do? Well, and this is kind of the trick, I guess. So if we have an array like this one, right? Well, if we compute the mid value, what do we compare this value to? We don't know what the minimum is, that's for sure. And even if we did, we don't know into which direction to go. So what you can do is you could compare this value with what values at the other side. So maybe at the beginning of the array. If you have a value that is larger than the value at index 0, so if nums at index 0 is larger than mid, so you could also say that. So if this value is larger than, let's say, 6, well, what does it tell us? That means the array is increasing in this range. So this is not where we want to look. We want to look in the other side, because the thing where we suddenly have a decreasing sequence of two numbers is on the other side. We know everything in here is going to be increasing. So if that is the case, well, we will say, what will we say? Oh yeah, we need to go left in this case, right? If nums is larger. Let me see. Yes, and if it's smaller, we need to go right. So if it's smaller or equal, go right. That means we're going to update our left pointer to be mid plus 1. Otherwise, yes. Otherwise, we need to go left, right? And the way to go left is simply set the right pointer to mid minus 1. Well, going left means that we assume that the smallest index is in here. Going right means that the smallest index is somewhere here. But whenever we go left, it could be that mid is actually our minimum, right? That's what that means. It could be our minimum. We don't know yet. So, so we have to kind of remember that, right? And typically remembering a value, and this is also when you insert something in an, how do you say, with binary search into an array, or if you want to insert that, you also have to remember the pivot element, which is the first or the last possible point of entry, depending on whether you insert a number larger or smaller than what you currently like. So we're going to actually remember this mid value. And in the beginning, we're going to set pivot just to 0. It doesn't matter. It's going to be updated anyway. We're going to return the pivot. So that's the index of the minimum element. When we go right, that means the mid value is not going to be our minimum element. But when we are, for example, here, when mid is pointing at 0, that means num0 is smaller or equal. It's not smaller or equal. It's larger than that value. So that value could actually be the minimum value. So we have to remember it. Same for here. So if we compare 4 with 1, means we're going left, right? And 1 is going to be remembered as our possible minimum value. And then going left means we're going to go look at this array next. And now we compute mid values maybe 6. Now we have to go right. And then we have 7. We compare 7 to 4. Means we still have to go right. And then left and right meet, right? So, but 0 is smaller. Well, it's larger. No, it's smaller or equal than, well, no, it's smaller than 4, which is the second case. So we have to remember mid. So that's how that works. I suggest you implement this, maybe go through a couple of examples to understand this. Certainly took me some time to do that. And yeah, it's one of those things that you just have to implement regularly to remember. Otherwise, to reconstruct it from memory is going to be tedious, going to be some work. All right, so yeah, I'm ready to give this a try. Let's see what happens. Hopefully I didn't make any typos. In my last video, I made lots and lots of typos and had to constantly fix it. Yeah, so I see we already made an error. Infinite loop because of why? Because we're not always updating our indices. Is that right? It equals mid minus 1. So that's a typo. There was a typo. Going to try again. Okay, and now you're running into typing errors, which is a sign of lack of concentration, but it passes. So now we submit this. And voila, there you go. So yeah, I'd recommend implement both approaches, the O of n time and constant space, as well as the one log n time with constant space. And you know, there are smart people out there who do both in one. you can also do that, but breaking these problems down into two could be extra points because you're approaching it a little bit more systematic. So you and maybe follow-up questions also become easier, you know. A follow-up question could be, what if the elements aren't distinct? You know, how would you deal with that case? If you needed to return the first index where something happened, where the target could occur, something like that. And in that case, then you also have to add a pivot element to your binary search, for example. So if the number is smaller than target, yeah, well, I forget. I have to implement it myself again to understand how, or to remind myself how the pivot works when you do it where you have non-distinct values in an array. But that could be a possible follow-up question, right? Right, yeah, so that's pretty much it. Again, thanks for watching, and I hope you implement this yourself.